So here we go. All right. See here we go. All right, we got a form here. Good. Okay, now, get done going through these concepts about the electron shells. There's one final chemical concept, at least in terms of electron shells, and so we'll start chemical bonding probably, well, we'll see how time goes, but we'll start chemical bonding probably tomorrow. But meanwhile, it's one other thing about electrons, electron shells, and things like that. This is a sometimes underrated concept in chemistry classes, but it's actually very important and helps one to understand why certain elements make the kind of chemical reactions they do, and why they have certain chemical properties, and why they react with certain groups, and why they make certain types of chemical bonds. And that concept is what we call electronegativity. Now, in a variety of chemistry textbooks that I've looked at, they usually devote a paragraph or two to it, and even less in your typical biology or biochemistry textbooks, but it's actually an important concept. So quick and dirty, what is electronegativity? It's how tightly a given atom holds onto its valence or outermost electron. So some atoms hold their valence electrons quite loosely, meaning they can easily be removed. Others hold them quite tightly. And electronegativity can be represented by a numerical scale from 0 to 4. We won't bother with that. You can see that in chemistry class and stuff. We're just going to do a line graph a little bit later. But a few general trends about electronegativity. You can draw the periodic table, or part of it, the part that we're interested in. Okay, we see a couple trends in electronegativity. The ones that have one valence electron tend to be less electronegative. In other words, they give their outer electrons up easily compared to ones with 2 or 4 or especially 6 or 7. So, things tend to get more electronegative as you go from 1 valence electron to, say, 7 valence electrons. So things like chlorine and fluorine hold their valence electrons very, very tightly. So that's one trend. But the second trend is this. As you go down the column from lighter to heavier elements, the heavier elements in the same column are less electronegative. For instance, hydrogen is more electronegative than lithium, and lithium is more electronegative than sodium, and sodium is more than potassium. The overall electronegativity of an element depends on the combination of these two factors, and we'll do a numerical line graph in a few minutes to show you about that. Now, another thing, a low electronegativity atom, like say sodium, it's easily loses that single valence electron. Magnesium and calcium lose their 2 valence electrons fairly easily too. But things like carbon and silicon hold them on reasonably tightly, and things like chlorine and fluorine hold their valence electrons very tightly. Now the other thing too is if you're a highly electronegative element, not only do you hold your electrons on tightly, you have a tendency of taking somebody else's electrons. It's like those guys on Wall Street that were giving out mortgages to people that could never possibly pay them off and then selling them off to unsuspecting victims and collapsing the whole global economy as a result. Okay, they're making tons of money, but they're not satisfied when they want to make megatons of money. They're greedy. Highly electronegative elements like fluorine and chlorine are greedy for other people's electrons. They're not satisfied with their 7. They want more, more, more. Okay, and they get that. So, you look and put electronegativity, at least with some of the stuff that we're interested in, and make a line graph, and there's numerical values, but we're not going to bother with it. We're looking at this at a conceptual level. So highly electronegative atoms are very greedy for other electrons. And weakly electronegative atoms are the opposite. So let's say here, electronegativity scale. Now keep this one in mind and the relative positions of things here, because that's actually very important for understanding chemical bonding and the properties of different kinds of molecules. If you know this scale and know this concept, the rest of it falls automatically into place. That's why we're putting this one and emphasizing this concept. Now, I think most people learned a little bit about this in chemistry. Depends on who the instructor is. Sometimes it's just mentioned in about 2 seconds. And oh, well. And you look at some of those chemistry textbooks, and they have a paragraph or so about this. But this is actually a very important concept. And it can help us understand a lot of what comes afterwards. So we have low electronegativity. Now some of the stuff that we're interested in, way down the bottom of the super WIMP here, of what we're interested in, about the lowest of the low is going to be potassium. Potassium, which has that electron shielded by a couple other electron shells beneath it, it loses that electron real easily. It gives it up at the drop of a hat, you know. Somebody comes up, can I have your electron? Take it. Okay. All right. Sodium is not far behind, and the lithium, which we don't have to worry about a little bit more. Now, surprisingly, when you go up to hydrogen, hydrogen's kind of middle of the road. Recall, hydrogen, although it has a single valence electron, in fact, it's its only electron, that electron is not shielded by inner shells, and it's quite close to the nucleus, so it's exposed to that positive charge of that proton without any protection. So hydrogen actually, for things with a valence of 1, hydrogen actually holds that outer electron fairly tightly. Okay, and then we have things like calcium higher up, things like calcium, and things like magnesium. Once again, calcium is less electronegative than magnesium because it's a heavier element, it's got inner electron shells. So they give their outer electrons up pretty easily too. Now, hydrogen and carbon are quite close together. I forgot the exact order, they're very close together. I'm going to put it here, it may be the other direction, but carbon with 4 valence electrons holds its electrons moderately tightly. And it's quite comparable in electronegativity to hydrogen, even though hydrogen just has that single but close-in electron. Now we go further up. Nitrogen, important in all kinds of biological molecules. For instance, nucleic acids in the building block, they have nitrogen in them. Amino acids that make up proteins, they have nitrogen. All living organisms need a source of nitrogen. Now, unfortunately, nitrogen gas does not count because breaking nitrogen gas down is very hard. Only a few microorganisms can do that. So everybody else has to get their nitrogen from other things, like organic nitrogen, things like eating proteins and stuff like that, or from things like nitrates and ammonia and stuff like that. So what's fertilizer? What's plant fertilizer? It's nitrates and urea, nitrogen-rich molecules. So what goes into fertilizer? Urea, ammonium nitrate, potassium nitrate, all those kind of things. What happens when large amounts of fertilizer catch fire? Look at Texas. Ammonium nitrate explodes in large quantities. Okay, but nitrogen's moderately electronegative. Notice it's more electronegative than carbon and hydrogen. Now, somewhere around that general area is sulfur, which has 6 valence electrons. Now, we go up to some other things. Oxygen is very electronegative. It's a relatively small atom, and it has 6 valence electrons. It holds those guys on tightly, and it also has a tendency of taking somebody else's valence electrons. Somewhat lower than oxygen is going to be chlorine. And then we go to the worst of the worst. This is the Bernie Madoff. of electronegative atoms. Fluorine, the most electronegative atom around. And it is so greedy even Wall Street would blanch at that. Okay. Now, interestingly enough, because a combination of small atom and having 6 valence electrons, oxygen is the second most electronegative atom around. It is very electronegative. It's even more so than chlorine. Now, does anybody have a swimming pool? Okay. You throw in that stuff to get rid of the algae and what have you, chlorine in the pool. You look at the label of that, whatever form that stuff is in, powder, liquid, it says, warning, oxidizer. Okay, what is oxidizers? Oxidizers, named after oxygen, are molecules or elements that take electrons from something else. So the process of oxidation is when something takes electrons from something else. And of course, originally the term oxidation meant combining with oxygen. But oxygen is not the only thing that can oxidize stuff. Chlorine can do it. That's why you see bottles of bleach and whatever, and bottles of, and canisters of poo chlorine says oxidizer, strong oxidizer. The worst of the worst is out here. Fluorine, because it's the most electronegative atom known, oxidizes things with even greater affinity than oxygen does. But oxygen, which is important in life, oxygen is the second most electronegative atom in the business. So, not surprisingly, oxygen likes to oxidize or remove electrons from other things. Fluorine does an even better job of that. Chlorine, not quite as good, but still pretty potent. I mean, you can do things, you take poo chlorine, we used to do this when we were kids, you take poo chlorine and you mix it in with sulfur and charcoal, and you mix the stuff in, and a little bit of potassium nitrate, and you mix the stuff in, stick a fuse in it, light it, and put it under an unsuspecting visitor stand at a football game, and you get this huge smoke cloud that has a nasty, bleachy, irritating smell to it. But because chlorine was a powerful oxidizer, if you left that thing in the container for too long, it would warm up and it could spontaneously ignite. That happened to a friend of mine who went off, his little smoke bomb went off in his pocket in the middle of school cafeteria. Quickly took it and lobbed it across the cafeteria. But, okay, so it tells you chlorine is a strong oxidizer, but oxygen is even more so than that. All these kind of stuff that can get me in serious trouble now. But at any rate, okay, fluorine is extremely powerful oxidizing agent, but oxygen is extremely electronegative. So it's involved in all kinds of oxygen or oxidation type reactions. Now, since we have time for this, so keep this electronegativity scale in mind. If you are highly electronegative, not only do you hold your valence electrons tightly, you also take somebody else's electrons. In other words, you oxidize those other things. If you're weakly electronegative, you lose your electrons at the drop of a hat, and you don't take anybody else's. Now you got middle of the road ones like carbon and hydrogen that are not neither weakly electronegative nor particularly strongly electronegative. So they're going to react with things differently than some of the other elements will. Now, imagine what would happen if you took something like fluorine, the most greedy electronegative atom in the business, and you put it next to something like sodium. A little wimpy atom that doesn't hold its electrons up very tightly at all. And then comes chlorine or fluorine. Give me your electrons. And yes, you can count them. Okay, that's what's going to happen. That's a type of chemical bond. And that's what we're going to lead to right now, is chemical bonds. The idea behind chemical bonds, now we're going to have hydrogen bonds, which are not, strictly speaking, the type of chemical bonds I'm going to cover in the next few minutes and continue on tomorrow. Okay? Hydrogen bonds are different. We'll see that later on, even though they're called, quote, a chemical bond. Not quite the same thing. The chemical bonds we're looking at today, the idea behind chemical bonds is you're going to do things with the outer or valence electrons. And this is what joins atoms together to make molecules. The basic idea of chemical bonds and chemical reactions that lead to the formation of new chemical bonds is that you're going to play around, do things with valence electrons in the atoms involved, and you're going to try to fill the outer electron shell, the valence electron shell, of all the atoms that are participating in this. Because it turns out atoms like to have filled outer or valence electron shells. If I ask you folks, what's your goal in life? You know, some people might say, I want to have 15 kids. I go, God, right? Okay, I know, I could imagine. Yeah, I could imagine. Or, you know, I want to be a doctor, or I want to be a lawyer and sue doctors, or, you know, I want to be a biochemist, or I want to be a nutty college professor, or something like that, right? Okay, you probably don't want that, right? Okay, at any rate, okay, I could ask you what your goal in life is. You come up with a whole bunch of different things. Now, if you could ask an atom what its goal in life is, it'd say, I want a filled valence electron shell. Because once you have a filled valence electron shell, you're nice and stable and happy. You know, so you fill your electron shell, you're in nirvana. Oh man, I got a filled electron shell.
Yes, yes.
Okay, it's going to be a real happy camper, right? I'll take a toke on some more electrons, valence electrons. Okay. All right. So, atoms.
We need to hang out after class.
Atoms try to fill their valence electron shells. That's one of the big goals in life of an atom. And the way they do it, if they don't already have a filled shell, if you already have a filled shell, you're a happy camper, so you don't need to make chemical bonds with anybody. You're a noble gas, you don't react with anybody. They already have filled valence shells. Everybody else, though, all the mere commoners on the periodic table, want to try to somehow fill their valence electron shells. And by doing it, they have to interact with other atoms, maybe one of the same kind, or maybe something different, and somehow, at least part of the time, fill that valence electron shell. And that means they do chemical reactions and they form chemical bonds. Now, the different types of chemical bonds, which in our case, in this thing, are ionic bonds and covalent bonds. The different types of chemical bonds are different ways of achieving the same goal. It's just some work for some kinds of combinations of atoms, but don't work for others, and others work for certain combinations, but not for others. So, chemical bonds are attempts for the atoms involved to fill their valence electron shells. The types of chemical bonds are different ways of achieving the same goal. Okay, so let's look at our electronegativity scale here. We're going to look at the simplest type of chemical bond, and we're going to hang it up today. All right. Let's take a look at sodium and fluorine. Okay. Sodium. We've got that single electron in that valence shell. And sodium holds that electron on very weakly because it's only very weak in the electronegativity scale. And then we have the greedy fluorine. I went for Wall Street. Okay. All right. So, it's got 1, 2, 3, 4, 5, 6, 7 valence electrons. It wants 8. It wants more. It wants a filled shell. So how can we do this? Fluorine comes up to the unsuspecting purchaser of crappy mortgage pools. Sodium, the very unelectronegative sodium. And what it does is simply steals that outer valence electron, because it is so weakly held that fluorine will grab it and run off with it. Now, it won't quite run off, it gets caught and punished. But what's going to happen is we're going to transfer this electron from the sodium to the fluorine. Now, fluorine has a filled shell. It's happy. I got more. Okay. But there's a little punishment. The SEC catches it. The punishment is this: it has one more electron than protons. You have not changed the number of protons in the nucleus, otherwise it would be something other than fluorine. So it has one extra electron. That means it is an ion with a negative charge. So it's a fluoride ion. Meanwhile, this sodium, it lost that single electron in the valence shell, so we're going to make that shell disappear. And what do we have underneath? We have a filled outer shell and that filled inner shell. So guess what? Sodium has a filled shell too. That's what it wants, but it has to pay a price too, and the price is being a positively charged ion. It's lost one electron, it's not lost any protons. So now we have these two sodium ion and a fluoride ion. The ions attract each other. They're opposite charges. They attract each other and they stick together to make sodium fluoride. And then you stick it into your toothpaste. And likewise, same thing with sodium and chlorine. Chlorine's not quite as electronegative, but it does the same type of things. You make sodium chloride. Now that is what we call an ionic bond, because you end up generating two different ions or more. You could have things like magnesium giving an electron to each of two chlorine atoms. And we have magnesium chloride or calcium chloride. Those are held together by ionic bonds as well. In this case, magnesium donates one electron to each of the two chlorines. Everybody's got filled shells, but the magnesium has a double positive charge. It gave up two valence electrons. Each chlorine has a single negative charge, and now you got magnesium chloride. Same thing with calcium. Okay, these are ionic bonds. Now, ionic bonds are formed when one atom takes electrons from somebody else, completely removes them. And the way to get ionic bonds is you have to have atoms that are opposites on the electronegativity scale. You have to have something that's so electronegative it can literally rip an electron away from its partner or partners. If you can't steal the electron completely, you cannot make an ionic bond. You have to go another route, and that other route's a covalent bond. We'll see that tomorrow. But an ionic bond, you have to have something that's so electronegative and something that's so weakly electronegative that the electronegative guy just takes its electrons. It's just like you may remember in the schoolyard or something. Okay, somebody wants to, steal your lunch bag or your wallet or your girlfriend or whatever the case is. They do that all the time. Okay, now, hey, I went to high school. I remember what it was like. Okay, now, if you got let's give it the Y chromosome. You got two guys and one of them wants something the other person has, whatever it is, and they get into a scrap. If they're evenly matched, nobody's going to come out of that in good shape, right? You're both going to beat the crap out of each other, and then, and maybe they'll even discourage people from getting into a big scrap. Now, on the other hand, if you got somebody that weighs 130 pounds and somebody that is a football player weighs 270 pounds, there's a little unevenness there. The football player could probably get away with whatever he wants, right?
Sodium should pick up a bat.
Okay, that's true. Bring on, what is it, a Tech 9? Well, that happened. That's what happened in Colorado. But anyway, without extreme firepower, generally the big guy's going to win, right? So he will intimidate you into giving up your valence electrons. Okay, so you have to have a real mismatch. You can't have an even match here. You have to have things that are very far apart on the electronegativity scale. So if you were to look at this, a zone where ionic bonds are typically made are from guys that are opposite ends of the scale. And this is an approximate kind thing, but this is generally the zone of ionic bonds here. In this case, highly electronegative atoms, such as chlorine, oxygen, fluorine, outright steal electrons from things with valences of 1 or 2, like sodium and potassium and stuff like that. Now, once they do that, those electrical charges, the opposite charges on the ions, glue them together, and they glue them together quite tightly. And you can measure, there's measures of how tightly a chemical bond is, and they call it bond strength, and it's expressed in kilojoules per mole, or the old kilocalories per mole, which is what I remember. I don't really went to kilojoules per mole. But at any rate, crudely, it's how much energy it takes to break a chemical bond. Now, when you look, and I'm going to use the kilocalories per mole, because I forgot whether you convert up or down to go to kilojoules per mole. But anyway, ionic bonds tend to be, 30, 40, 50 kilocalories per mole. Covalent bonds tend to be much stronger, generally about twice as strong as an ionic bond. So, ionic bonds are relatively strong, but they're not the strongest bonds around. And an indication of bond strength is how much heat it takes to break them. Now you can take salt, sodium chloride, an ionic bonded molecule, and heat it up, and you have to get it almost to blast furnace temperatures for the crystals to melt, and then you have to get it up to blast furnace temperatures for the ionic bonds to actually break. And many things are held together by ionic bonds are common minerals, things like calcium chloride, calcium fluoride, calcium carbonate. Carbonate actually is an ion as well. A lot of these different types of ionically bonded molecules are common minerals that go into many kinds of rocks. Not all of them, but many are. Now there's an interesting thing though about ionically bonded molecules. Although it takes a great deal of energy to break an ionic bond simply by adding heat to it, there's one molecule, actually several, but one molecule we're very familiar with, that has a remarkable ability of making quick work of breaking ionically bonded molecules, or at least most, but not all of them. And that molecule is water. And we'll see why later on. But when you take salt, sodium chloride, an ionically bonded molecule, you throw it into water. What you end up with is not a solution of sodium chloride molecules in water. You end up with a solution of sodium ions and chloride ions separate from each other, but in the water. So in other words, water has broken apart the ionic bonds of sodium chloride. And likewise, if you take sodium fluoride, put that in water, that dissolves at fairly high concentrations. Magnesium chloride, magnesium fluoride, they're quite soluble in water. Every time you dissolve a salt in water, that water is somehow breaking those fairly tough ionic bonds. We'll see why later on, but keep that point in mind. So, we see one way of doing chemical bonds and filling everybody's valence electron shells. And that way is for one atom, a highly electronegative atom, to just be a big bully and steal electrons from a very much unelectronegative atom. But what happens when you have atoms that are roughly evenly matched? They cannot steal electrons from each other. They have to come up with a different way of filling their outer shells. And that way is what we call a covalent bond. And that's what we're going to see when we come back tomorrow. So I'll see you guys in lab. All right, 15 minutes.